Okay, thanks. I try to squeeze now in 15 minutes something like 10 years of research. So let's see how this goes. The reason why I chose this topic is that it's more like a story, not really like research, but kind of a story how we ended up considering certain mathematical objects and how they were motivated actually by numerical computations. Part of this whole FAME flagship is that we try to combine theory and computations and experiments. So I thought that this is a reasonable way to give this presentation. Here's the outline of my talk. So first I will consider something that I call principal component reconstructions in EIT. You will see fancy pictures at that point. Then I will relate these fancy pictures to something called Zernike polynomials. And then I will present some infinite dimensional stability results for electrical impedance tomography. Those of you who are not that familiar with the Calderon problem won't probably understand all the details, but I try to at least give some ideas of what's going on. Then I will present a direct reconstruction algorithm that uses these Zernike polynomials, and finally I will return to numerical experiments on actually experimental data. What I mean by principal component reconstructions in EIT. First of all, here's a picture of typical EIT, electrical impedance tomography experiment. So this is a water tank from University of Eastern Finland at Kuopio campus. There are a couple of inclusions inside the water tank. Then there are 16 electrodes attached to the interior surface of the water tank. And the idea is to apply current patterns between these electrodes and measure the corresponding voltages and reconstruct what's inside the tank. And typically you get some kind of blurred image of this kind of inclusions. I will at the end show reconstruction. And what we tried numerically is the following. This is something like year 2015. This was a collaboration with my doctoral candidate Lauri Mustonen. So we draw random log normal random fields realizations of random fields that were log normal and use those as conductivities for this kind of disc-shaped object. Then we used complete electrode model, which is an accurate model for EIT measurements to simulate measurements for 16 electrodes. It is actually exactly the shape, the tank shape is exactly what was shown on the previous slide. And we used 15 trigonometric current patterns for these simulations. So after that, we had a family of measurements simulated for this kind of water tank-like objects. And then these measurements can be interpreted as symmetric measurement matrices. And what we did was taking logarithms of those matrices. So you don't have to understand what the logarithm of matrix means, but that can be done by taking the logarithms of the eigenvalues. And then we performed principal component analysis with respect to the Frobenius topology for these measurement matrices. So the matrices that give all the measurements in certain bases for these electrode measurements of EIT. And then what we did was that we used each of these principal components in turn as the data that was used for computing reconstructions in EIT. So we considered each of the principal components that kind of give you the most typical measurements that can be obtained if the prior for the conductivity is log normal, and computed the reconstructions by using Bayesian analysis, essentially with the same prior that was used for drawing the conductivities. And these were kind of computed in the standard way by minimizing Tikhonov type functional by Gauss-Newton method. So these try to be maximum a posteriori estimates for that kind of simulated measurements. And what came out of this experiment was this kind of patterns. So at the top left corner, I have scaled this a little bit poorly, these reconstructions, but the top left-hand corner is not quite constant, but it's close to being constant at reconstructions. So these are reconstructions from difference data when the difference data correspond in turns to these principal components that we considered for the logarithms of the measurement matrices. And as you can see, there are certain patterns. So you have different oscillations in the angular direction. And then when you go further into these modes, you have oscillations also in the interior of the object. There are also kind of some of the reconstructions where rotated versions of these ones, and some of them weren't as easily interpretable as these ones. But anyways, this was kind of interesting that we were able to obtain something that had this kind of patterns by just using random draws from log normal conductivities. And then we actually didn't use this for anything because we ended up noticing that the original idea was to build some kind of surrogate, polynomial surrogates for computing inversions or reconstructions in electrical impedance tomography. But it turned out that it's more important to consider how you linearize the problem, sort of whether you take some transformation before linearizing than using the correct basis. So these were kind of forgotten for some time. However, regarding Zernicke polynomials, already in 2017 or something like that, Lauri Mostonen once came to my office and said that he knows what these patterns are. And he showed me this kind of picture. It's not necessarily exactly this picture, but anyways, it was Zernicke polynomials. And if you compare these objects that are well known, let's say in optics community, with these reconstructions, you can't be, of course, sure that these are exactly the same things, but at least the patterns are pretty similar. And then it was kind of an interesting phenomenon to notice, but we didn't do anything with this at that point in time. And then time moved forward, and I ended up, okay, here's definition of Zernicke polynomials. So I don't assume that you can actually understand what's going on over here in detail. The main thing is that there are two parameters, J and K. K controls how much activity there is kind of in the radial direction. The larger K is, the more there's happening in the interior of the object. The J parameter corresponds to the angular frequencies. So this is just Fourier modes in the angular direction. And the exact definitions for these normalized orthonormal Zernicke polynomials are like this. And these form a basis for L2, and we can have this kind of decomposition of the L2 space on the unit disk D by considering fixed K and taking the span, close of the span over all angular frequencies. Okay, I didn't even pay that much attention to these formulas back in the day, but then we started to consider with Henrik Karde stability results for electrical impedance tomography. And what happened was that we were able to quite neatly show that for the linearized electrical impedance tomography problem, if you assume that the conductivity perturbation is a harmonic function, then we get nice stability result for the linearized problem. And then I just mentioned to Henrik that, okay, at one point in time, we considered things that were called Zernicke polynomials, and maybe we could, because the zeroth order Zernicke polynomials in this K index, they are exactly harmonic functions. So maybe we could use these Zernicke polynomials to actually do some theoretical considerations. And this actually turned out to be quite fruitful. So first we considered linearized EIT problem. So you can think about what's the linear approximation for the change in the boundary measurements when you perturb the conductivity inside the tank. And we using Zernicke polynomials with different groups of people, also with Joanna Bish, Markus Hirvensalo, Antti Autio was involved in some of these parts. We were able to prove that if you fix this K parameter, which is kind of tells you how deep inside the object the perturbation is active, then we were able to first of all prove that the linearized forward map of electrical impedance tomography is continuous from L2 to Hilbert-Smith operators on the boundary on L2 space, and also that we get Lipschitz stability for each fixed K with actually rather explicit Lipschitz constant. And that this was nice. And then we started to consider whether we can do something for the non-linear EIT problem. And this is something that you definitely can't understand, but the idea is that also using these Zernicke polynomials in actually any dimension, not just two dimensions, you can introduce infinite classes of conductivities for which you actually get Lipschitz stability. So for general, like just smoothness classes, you can't get more than logarithmic stability, but if you restrict somehow the behavior of the perturbations inside the object or the conductivity inside the object, then you actually can get Lipschitz stability with, once again, rather explicit Lipschitz constant. So if somebody is more interested in this theorem, then I can explain it offline. Finally, this linearized problem or linearized result was accompanied by a reconstruction algorithm that is actually totally direct and explicit. So here it is. So if the conductivity perturbation is given in the Chernigke basis, like over here, so C, J, K are the coefficients. Chernigke polynomials are L2 orthonormal basis. So you can present any L2 perturbation like this. And here you can see the kind of combinatorial formulas, how you can compute the reconstructions. Interesting things are that the angular frequencies are totally disconnected, so you can consider each angular frequency separately, and this formula actually corresponds to forward substitutions for solving for each fixed j for solving a infinite triangular system. So this can be implemented. It's very, very cheap. It doesn't plotting reconstructions costs more than computing the reconstructions. And you can actually, by interpreting electrode measurements correctly, you can actually apply this to EIT data. So let's go back to this example with the water tank. First, this kind of a sanity check that if you have ridiculously accurate difference data, then this is the reconstruction. The difference data is non-linear, so that's not linearized. But we get this kind of reconstruction with the linearized reconstruction algorithm that is pretty much perfect, and also the dynamic range is pretty much accurate. And you can also go to water tank measurements, so you get this kind of blurred reconstructions. But anyways, you can apply this to 16 electrode measurements if you interpret the electrode measurements correctly. So you can go from numerical simulations to Chernigke polynomials, and using these Chernigke polynomials, you can apply this kind of reconstruction algorithm, and you actually get reconstructions from experimental data. And here are the references, and I'm ready for answering questions.